Hello everyone. I'll be talking to you about IPv6 in this presentation. And my outline, my talk is motivation, IPv6 highlights. And I'll be going through the IPv6 packet header. I think that's the best way to learn about IPv6. And I want you to think about how is it different from IPv4, right? The IPv6 addresses, okay? So basically the IPv6 motivation, as you know, why do we need the IPv6? What do you guys think? Okay. I mean, some of you are thinking the possibility of running out of IP addresses, you know. So, we have all the IoT devices, even, autonomous vehicle, you have your phone. So number of IP addresses, because running out with the IPv4 is so limited, right? So that's the one aspect of it. And another thing is a flexibility. IPv4 is not that flexibility. It doesn't even consider the, QoS and also the security part. The IPv6 does. And I'll be talking to you a little bit about it. Okay, it's a long time ago. I know we're at the 2023, 1990, IETF began to work on the version of IPv4, v6. So IP address seemed to be exhausted faster than expected, and now it's even faster because number of IoT devices is rising. So one of the problems is IPv4 addresses is it has class A, class B, class C. Okay, but a lot of the small companies, they go with class B because with 56,000 hosts. I mean, when you look at the Class C, and Class C has only a 256 host. I mean, not many company wants to use a Class C because so small. So they think that it's gonna be a lot more than 254, even though they don't have a lot of IP addresses being used. So utilizing Class B. And there will be a lot of ways. Let's say there is only 300 hosts, and the 56,200 are being wasted, right? So what I'm saying is IP addresses for V4 is not, efficiently designed, and there are limited, IPv4 out there. A lot of company wants that, even with a small company. Okay. So another thing is they wanted to simplify the protocol, because if you simplify it, whenever you arrives at the hub, it tends to process faster, right? It tends to process faster, simpler you did. So you don't want to make it too complex, and it has to do a lot of thinking, processing slow. You don't want that, okay? So you wanted to have IP protocol is a pretty simple, and it can address as QoS, or it can do multicasting, mobile host. It also includes a security, and with different header option. I'll be talking to you more about this. Okay. So RFC, this is a long time ago, 1550 invited proposal for IP next generation. There were 7 proposals, and they standardized IPv6 back then, okay, out of 7 proposals. So highlight of IPv6 is a connectionless like IPv4. It has a huge address space, and it feels that they have enough addresses to last for a long time. And another thing is, remember I told you about the QoS multimedia here. So it supports a real-time application, voice and video. And it was a challenging for IPv4. It has to have a different protocol and work with it, okay? So another thing is a fragmentation. And when you look at the IPv4, as it transfer from one router to another router, any of the router could, fragment it, make it smaller, and make it smaller, and later on they put it together. But in the IPv6, you can allow to do it at the sender, not at the middle of the transmitting. Okay. So header equals a base header, there's optional extension. This is what I mean about the flexibility of the header. Instead of IPv4, it has a header options. If it's not used, it one has just a dummy field in there. So that was very inefficient. Okay. So it has a base header. It tends to be smaller. You can add on the extension header as you need it. Like as you need it. Okay. Here's a base header. You can add the extension header as you need it. So that's the difference. It creates a lot of flexibility. Let's take a look at the IPv6 header. And first bit is a version number, just like IPv4, it does have that. But in this case, it has a class. It's an 8-bit class, and the D stands for delay sensitive. Is it delay sensitive? It's like a video, okay? And P stands for IPv4 precedence field, and R stands for reserved. IPv4, it has a different priority. 2 to the third is you have 8 different priority you can have because there are 3 bits, right? All right. So you could have different classes. Okay. So another thing is very interesting here is the next item is a flow label. You could have a flow, dedicated flow from sender to the destination, which can be very useful to meet the QoS requirement. So flow label is experimental, is very vague, but it's built for IPv6. It's basically end-to-end stream packet with the same particular requirement. It's basically for QoS reserve bandwidth. It has a very strict delay. Basically, when you drive on the highway, all the right lane is dedicated to you. No one else can use it. That kind of mentality, right? So flow label tends to have the source address, destination address, and there has to be a flow number. So once it receives that hub, if it's look at the flow ID and flow number, it doesn't have to think much. It just send it to the next hop of the flow. Okay. So basically that's what I'm saying. Router doesn't need to look at the IP header. You just look at the flow ID because this is more of you set it up first, then you send it down. So you need to look at the flow ID on the table to find out how to handle the packet instead of utilizing extra field from the header. Okay. So one good thing is if you have it, you can use it, which is make it very efficient of processing each packet. But if it doesn't, you can just ignore it, okay? You don't have to use it. Again, payload length is as you indicated, how big is your payload? 64 kilobytes. The payload, what does it mean is how big is your data you're attached to this, this packet, okay? That's, payload. Next header, this next header makes it more flexible. Okay, remember I told you that there's a base header and that there is all optional header. So next header indicates what are the optional header being used. Okay, like a optional header you need to use for like a QoS, security, and all those items. So next header indicated whether there is optional fields are being used. Okay, so to know what is the mean is if it's next header, if it's one, the optional header extension is ICMP v4, and if it's 4 is IP and IP tunnel. 6 means TCP header, 17 is UDP, and 43 is a routing header. It's a routing overhead. Okay, there's a fragmentation header, authentication header, and there is a encrypted security payload number 52. And 59 indicate there is no next header. So base header is that's all you need. That's what's indicating. Okay. To give some more graphical example, if you look at something like this, so next header, if you allow extension header to be chained, right? For example, if the next header is a 43, and that means the next header is about the a route header, which hop it needs to go, right? So if it's the next header is 51, if it's being used on the next one, you can continue to add on additional header. 51, that means it's authentication header. Okay, and next header 6 means a TCP segment. As you can see, you can have a bare minimum, but whatever you need, the additional header, you can add on to top of it. Make sense? Recommended header, next header, typically appears in this order. Hop to hop option is first, destination option, routing, fragment, authentication in this order. Okay, because the higher protocol is the last, because that indicates the what's upper layer protocol is being used, whether it's a UDP or TCP. Okay. So hop by option is IPv6. It has a hop by hop option, and just like IPv4, it does have that. So you could have a routing header, which means at least all the router needs to be visited. Okay, to do this, it needs to be set up in the first. Okay, it should set up. It should be established with the routing header first. Then you can have a routing header. Okay. So there's no flexibility. When it's a router header, you need to follow the route list of router is specified there. That's more of a strict routing, and the loose routing is so only selected routers are specified. As you go to the selected router, but it does have a flexibility, go to left, go to right, and a little bit, and until you get to the next specified header. It's more of a loose routing. Okay, strict routing tends to have a higher QoS built in. Okay, so fragment header is contain datagram, fragment offset, midfield bits. Only source can, and like I said, not in the middle of the router. Only source host can fragment. Router cannot fragment it, as I indicated. That makes a really simplifying process at the router. It doesn't need to fragment it. Fragment it takes a good amount of time to do that. So that means it's a faster router processing. Okay. Next is authentication header. Basically, the authentication verifies sender's identity. Okay. So part 1 is the next header number. That's the authentication header. It needs to have a 4-byte key. And part 3, it needs to have a checksum. So senders and receivers shares a secret key assigned to 4-byte. That's assigned by, it could be assigned by the security node. Okay, or it can generate that 4-key byte itself, but that generated key needs to share with receiver as well. Okay, you may need to establish a connection before sending it. So sender computes a cryptographic checksum of a secret key and packet and the secret key as well. So receiver finds the secret key from the key number, right? It recomputes the checksum. It goes in the reverse order, and the secret key receive packets, and then you'll try to match. If checksum equals the checksum in the authentication header, what it came with, then sender identity is verified. Means it's sender identity is who they think is is correct. So to do that, they need to make sure they'll calculate the checksum is computer checksum is same as checksum in the authentication header. It came with it. Okay, but if it's different, that's a big problem, right? So encrypted security payload header is information about encrypted payload. Information depends on particular encryption algorithm being used. If it's a heavy encryption, it tends to be a longer head. Okay, it's much more dynamic. Destination shared header indicate the packet handling of preference. It needs to be defined, like it needs to be a pretty strict. You don't want to lose any packet, which is a very high priority to do that. Okay. So let's go back to the IPv6 header, and hop limit is 8-bit. So you don't want to make the packet going around circle. Okay, if it's going around circle, you hop endlessly. So you put the hop limit, you hop up to a certain number of a hop that it doesn't get to the destination, you assume that this packet is lost. So you will terminate it, okay? So hop limit is important. You don't want to have, circling packets everywhere. So like I said, one unique thing about IPv6 is to look at all these source IP addresses here and destination IP addresses down here. So they made plenty of room to make sure that the IoT devices, all devices have IP addresses. You don't have to use the network address translation, because a lot of the company does not have enough IP addresses uses net, right? So it's both of them are 128 bits. Instead of describing a decimal notation, as you can see, it's pretty long, right? It's pretty long. So instead of utilizing decimal notations, they decide to go with the hex notation, which is a lot shorter than decimal notation, right? So that's why they use more of a hex, So I want you to know that the IPv6 address has 3 types of addresses, and there's a unicast, is a one-to-one, is a multicast, one-to-many, okay, group of destination group of host. A lot of times, one-to-many is if delivering some a tutorial material, video or something, so you can do multicast, okay? So anycast is, somewhat, this is kind of new to IPv6. So you just send it to anyone in the group, destination group. So if you just send it to anyone in destination group, and that any node that receives that packet, that node would broadcast again to everyone, then the and then it can distribute to everyone. But typically you don't have particular node that you wanted to contact. It's just any node will be fine within the cluster or group. So that is one of the interesting item in the IPv6 addresses. Okay. So division of IP address space, they divide it up into, when you look at IP addresses, you kind of know what is link local unicast addresses. Okay, so you need to have 1 to 1052 1023 different unicast local link addresses in the site local unicast addresses, 1023 as well. So you can have a different division of address space. Then looking at the address space, you kind of know is NS AP addresses or IPX, different addresses as well. So compatible with the IPv6 before addresses, which is 0000, okay, and Oh, okay. To be used as IP addresses in the IPv6 header. So you're not going to be losing a lot of the, front part of the conventional IPv6 addresses. So having the, all zeros and having FFF, here 16 bits, that will indicate that this is IPv4 address, and then you have 32-bit of IPv4 address. Okay, so it needs to have FFF here, right in front of it, IPv6. So you recognize it's IPv4 address. Okay. So big question is, we have been transitioning from IPv4 to IPv6 for quite a while. There were a lot of talk 15 years ago, transitioning, 20 years ago, transitioning. But it's not really happening, quickly as quick. I mean, in this country, United States, a lot of places still using IPv4, and it's very slow to convert to IPv6. Their mentality is if it's not broken, don't touch, right? But a lot of the technologies, willing to upgrade to IPv6 because it offers so many features, and the network can be utilized very efficiently, effectively for the future. But some places they're resisting to adopt new protocol. Okay, so to adopt the protocol, you can't do all the take out all the IPv4 router, put all IPv6 router there. It's not possible, right? So you got to do more of a a smooth transition. So with a little bit of time, they increase the IPv6 router later with time, coexist with IPv4. That's the way to go. Okay, to coexist. So there are two different approaches, and having a dual stack means that it does understand IPv4 and IPv6 protocol. So yeah, understand it can process as an IPv4 packet, it can process as an IPv6 packet. It can do both, okay? And so that's a more of a dual stacking router. Of course, that tends to be more expensive, right? So another thing is creating a terminal. Like I said, there's a flow. You can create terminal IP, within IP, in the internal through IPv4. If there's a lot of IPv6 routers, but there's in the middle there's IPv4 router, you can create a terminal so that it can go across as an IPv6, a router through the tunnel. Okay. So it's taking some good amount of time, and one of the big thing is, remember we had a pandemic that kind of stopped it, and that in transitioning to IPv6, its cost is astronomical. So who's willing to pay for those, right? So when we had an economic hard time during pandemic, it was pretty hard. So my thought is that they will continue to evolve to IPv6. They need it because a lot of the IoT, like autonomous vehicles coming, even drone coming. So we need to have IP protocol that meets the current today's demand, being able to provide QoS, being able to provide reliability, right? Those kind of things. So IPv6 is a very, very important in the future. So I hope you learned something. And thanks for listening for this lecture. Okay.